Let's get started today. Couple of announcements. First of all, I have to cancel office hours today. I have a faculty meeting that was called, so need to attend that. I am tentatively planning to reschedule those office hours for Thursday from 4 to 5. So tomorrow 3 to actually 3:45 because I have a off-campus appointment at 4, and then Thursday from 4 to 5 will be my office hours this week. Second thing, a reminder that the test is been moved to after spring break, so don't have to worry about that just yet. And I'll probably briefly talk about what to expect on the test next week, but it's too early to worry about it this week. And today we are going to be finishing up our introduction to lists, iterators, and double-ended queues, which are what is the name of Deques. Also, before we get started, I just want to, again, kind of emphasize how you might incrementally build programs, because both I and the TAs are seeing a lot of instances where you're still developing your entire program before you're starting to actually debug it. And the second thing you're doing is you're exclusively relying on Dr. Plank's scripts to do your debugging, which is his scripts are often long and involved, and so they're not necessarily the best thing to use for debugging. So instead of doing that, I just want to reiterate that the best way to develop these programs, especially as they get more complicated, and they will as the semester progresses, is to develop them a few functions at a time. So in the current lab, actually let's go to the current lab, lab 5. So last week there was a whole bunch of functions that you had to write. So you had to write some bit matrix functions, then you had to write some functions for summing and doing a product in a submatrix, and then you had to do these hash functions. So you kind of had 3 different tasks. You had to write the bit matrix methods, you had to write the various arithmetic operations on them, and then you had to write the hash functions. Now, we said that the arithmetic ones, sum, product, submatrix, and inverse, aren't due until this week. So clearly you could put that off. That left the bit matrix and the hash ones. Now, Dr. Plank gave you some starter code. So he'd written some of the functions for you. The important one he'd already written for you was the print method that would print a matrix. That was very helpful because it allows you to print out any matrix immediately after you have modified it. And most of the operations you need to write modify the matrix. So what my suggestion is you start as simply as possible. And if you look at what he gave you, he also gave you a bit matrix editor that had a bunch of commands. The simplest of them was simply one that creates an empty matrix. Okay? So what I did, actually, when I wrote this, is I started by figuring out which of those bit matrix class functions were required for empty. Okay? So actually just think about it, you've done it now. If you're going to create an empty bit matrix, what are the functions that you're going to have to probably write? The constructor. And for print, what does it need to have in order to work probably? What's it going to have to do? Which function is it probably going to have to call? Here, I'll show you the functions again. Which function do you think that print is probably going to have to call? Probably rows and columns and val. So probably the first functions that I would write would be the constructor, the rows, columns, and val, because those are probably what print and empty need. Okay, I want to be able to print a matrix because that's going to allow me to do debugging, and empty is the simplest one. So those are the first functions that I wrote. And then rather than trying to test them using his scripts, I just actually created easy ones of my own. So I created a, say, empty 3x5, and I immediately print. And that tests all of my 4 functions that I just wrote: the constructor, the rows and columns, and the val. If empty crashes, then I know it was in the constructor. If print crashes, I know it must have been because of columns, rows, or val didn't work right. Okay, so I know exactly where to look for my error. And also, rather than running Dr. Planck's long convoluted scripts, I'm just developing simple examples of my own to try. Okay, and I'll try a few others. He said, what happens if I create a 0 by 0? Okay, well, it prints out an error message, so it doesn't work. But you want to test those cases as well. So before you move on, make sure you test the cases that he warned you about. Okay, so test your error cases. Okay, and don't just test one, test a couple, and print. Okay, so now I think that's working. Now I can move on and see what else seems simple. Well, the next simple thing is probably set, being able to set a row and a column. So to implement that command, which function or functions up here do you think need to be implemented? I heard it. Say it out loud. Set. There's one function that exactly corresponds to a set. So the next thing I did was implemented set, and I did the same thing. I started putting these commands in a file so I could copy and paste them, but I again did empty 5.3, and now I did a set. So set, say 0, 0 to be 1, and I immediately printed to make sure it worked. And then I did some more sets. I'll set 3, 2 to be 1, and print. And there it is. Now let's set it back, 3, 2, 0, make sure I can set it back to 0. There we go. So I'm doing some simple checks with set. Now let's do it for an out of range. 6, 10, 1, R must be less than 5. So making sure that this works for things that are incorrect. 3, 2, 5. Okay, so I check it with different errors, and if anything goes wrong, I know it's got to be in the set method. Gotta be. Okay, so once I get set working, I again look to see what his next command is, and it's swap. Okay, so swaps, in fact, he even tells you swaps using swap rows. So the next member function I'd implement would be swap rows, and again, I just test it. So let's swap up here 0 and 3. So you can see 1, 0, 0 is row 0, so it should become row 3. And sure enough, it works. But if I had a seg fault, I almost certainly know it occurs in swap rows because it's the only thing that is new. So at each point, it's a lot easier for me to debug because at each point, I've added only a little bit of additional code. And rather than using Dr. Planck's complicated scripts, I'm just using simple examples that I created myself to test it. And I'm doing some exhaustive testing. I'm not just doing 1 or 2 examples, but I'm doing several examples to try to cover all the use cases before I move on to the next function. Okay, and occasionally I do run his grade scripts just to see how many cases are correct. Okay, and if something is but the problem is it's often hard to know unless you look into his scripts whether you've implemented if something doesn't work, you're not sure whether it's because you did something wrong or whether it's because you simply haven't implemented that function yet. So I typically did wait until the end to test it unless he specifically said, these cases test this part, these cases test that part. But the thing is, by doing these simple tests, usually my program worked almost completely. On like 95 of the 100 test cases, it worked. Okay? Then I could concentrate on debugging the 5 that it didn't work on. And yes, at this point, I have to deal with his complicated scripts and the whole program, but it's a lot easier than writing the whole program and then running his script and it fails on the first one and you have no idea where the failure was because he has a whole bunch of commands in that script. So it really does help if you just develop this thing incrementally, a little bit at a time, and also test using simple test cases that you devise rather than complicated test cases that he devises. The test cases he devises are meant to rigorously test your program, to really throw it around. That's not how you initially want to test your program. You want to gently test it with simple stuff. So that's, again, I'll just probably come back to this multiple times during the semester. Incremental development and testing will really save you a lot of time in this course. Yes?
Which executable would we be running to test our code outside the grade script?
So it compiles. So when it compiles. So when you run make, it compiles into something called bit matrix editor. Okay? So it actually, he says that the testing program. Okay? So if you read, he's written this thing and it creates when you type make, it creates a program called bit matrix editor. Okay? And then he actually gives an example of running. He gives multiple examples of how you can run it from the command line. So he actually shows you examples of running it with simple examples. Okay? So that's what your program compiles into. And you can even, he has an executable in his own directory called bit matrix editor. So you can, if you have any doubt or question about what the correct output should be, you can run his program to see what the correct output should be. And then you can run your program to see if it's producing the similar output. So for example, as you've noticed, he's really not keen on telling you what his error messages are. So you almost have to run his program to figure out what error messages he wants to print. Okay? So, but that's the answer, is it compiles, in this case, into a program called bit matrix editor. And then if you execute those commands, which he's described, you can see what's going on. So it's an interactive editor. Okay? And he's written all that for you, that editor. So you only have to concentrate on writing bitmatrix.cpp. You don't have to. You're going to get into that a lot in the real world when you're working with teammates, is that you're just working on one piece of a project and other people are working on different pieces. So that's something we're also trying to get you used to, is just working with one piece and comfortable with the fact that you don't necessarily need to know how his program's written, because he's given you right here what we call the API, the Application Programmer Interface. So he's told you how you can use it. Okay, so you don't have to know how he wrote it. It's immaterial how he wrote it. You just have to know how to use the commands. And I do realize that requires that you maybe have to be able to intuit what functions he's calling. Okay? So it doesn't hurt to be able to go into his program sometimes and be able to look for stuff. So for example, he does provide it. You can look at it. If you go to Planck CS140 labs lab 5 and you look at bitmatrix editor.cpp, it's there. And you can look for empty, and you can kind of, it's, you know, I don't expect you to know anything what's going on here. This is clearly unrecognizable. But what you can see there is what he's calling. You can see that when he's saying if it's equal to empty, he's calling new bit matrix. So you can see at least which functions he's calling. If you can't intuit it, you can actually go into his code, and you don't have to even understand what he's doing. You can just look at his function calls to figure out what parts of your code he's testing. Okay, so, and by running his code, you kind of, it becomes less abstract too. Okay, so other questions? Okay. By the way, notice in all of this that hash functions weren't required at all. So actually, I was able to write pretty much swap plus equal PGM without ever having to get to my hash functions. It's only when I got to store and to recall that I actually had to worry about writing my hash functions. So the hash functions were something that I actually did toward the end of the first week's exercises. So at any rate, okay, moving on. Remember last time that we introduced a new data structure called a linked list. Okay, so previously we had only looked at vectors. Now we have this new structure that allows us to point to different nodes in the list using pointers. And we indicated that the STD, or Standard Template Library, STL, has a implementation of a linked list that can be found in the list library. And you may remember it actually has what we call sentinel nodes at the beginning and end of the list. So we call these sentinel nodes. So your actual things like, say, grapes, cherry, soda, those are items in your list. At the beginning and the end, we have sentinel nodes. And we introduced this notion of an iterator, which is an object that is able to traverse our list. So it's essentially a pointer to the list. Okay? And that iterator is declared by saying something like list. Well, let's actually look at the code. So here was a sample iterator, and you could get to the first element in the list with the begin command. The end actually does not point to the last item in the list, but points to the sentinel node at the end of the list. With lit++, we advance the iterator to the next element in the list. And with starlit, the dereference operator, we return the value that that iterator currently points to. Okay, so if we have a list, dot begin returns an iterator that points to the first element of the list, and dot end returns something that points actually to the sentinel node at the end of the list. It does not point to the last item in the list. It points to the sentinel node at the end of the list. Okay, so initially lit would point to the first item in the list, and then when we say plus plus, it advances to the next element. And then we also talked about the fact that you can iterate through a list in reverse, but now instead of using begin and end, you use R_begin, and R_begin actually returns an iterator that points to the last item in the list, and .rEnd returns an iterator that points to the sentinel node at the beginning of the list. And one counterintuitive thing about reverse iteration is you would think intuitively that you would use the subtraction operator, but for whatever reasons, when you iterate through a list in reverse, you still use the increment operator to move to the previous item in the list. Okay, so does anyone remember what the big advantage of lists were over vectors? Why do we, since vectors have been so easy to use, this doesn't seem to be, the notation certainly isn't as attractive for lists as it is for vectors. Why should we go through the inconvenience of using a list? Because we can put things in the middle of a list efficiently, whereas we cannot efficiently put things into the middle of a vector. Okay, so that's why we care about lists. Okay, so one thing that you can also do efficiently with lists is not just insert in the middle, but you can insert some things at the front of a list. So with a vector, you can only efficiently insert things at the end of the vector, and you can only efficiently remove things at the end of the vector. But with a list, you can efficiently insert anywhere into the list, whether it's the end of the list, beginning of the list, the middle of the list. So there's this method for a list called push front that will add something to the front of the list. So in this case, we were wanting to reverse a list, or reverse the elements of a file. So if we had 10, 20, 30, 40, we created a list, and what we did, we read them one at a time, and what this code did, by pushing always onto the front, we'd read 10, put it on our list. Then we'd read 20, and 20 would be added to the front of the list. Then 30 is added to the front, and 40 is added to the front. And you see, by always adding the next element we read to the front of the list, we naturally reverse the list. And now, using our iterator, we can run through the list and print out each of the strings that we read. Thus, we print the list in reverse order. Okay, so that's a quick review of what we did last time. Now, that does not account for the beautiful things that we can do with lists, which is that we can insert into the middle of a list. So let's say that we have a grocery list. Okay, so here's one that is oranges, bananas, milk, orange juice, and we want to insert yogurt before milk. So we want to put yogurt right here in our list. So I want to write a function that's going to insert a string into the middle of this list. So I'm calling my function down here, insert item, and here's the new item that I want to insert. Okay, this is the item that I want to insert before. So target is the, in this case, yogurt represents my new item, and milk is my target. I want to insert yogurt before milk. And then here's my list. Notice that I've taken care to declare it as a reference parameter. I would do this even if I did not intend to modify the list, but in this case I intend to modify the list because I want to put yogurt before milk. So the first thing I need to do is I need to find milk so that I can insert before it. So the first thing that I'm going to do is I'm going to do a linear search through my list looking for milk. Okay, so I get my iterator here, and while I have not reached the end of the list, I increment it. And each time through, I check to see whether I have reached my target. If I reach my target, I can do my insert. And you can see here is the insert command. So this is a new command. So you give it the iterators and the item. So what it does is it inserts, or it creates, a new node that stores new item and places it, or inserts it, this node, before the node pointed to by lit. So it inserts it before the node that lit points to. Okay, so if our list is, I'll just abbreviate, bananas, oranges, milk, orange juice, then lit points to milk when we do the insertion. It creates a new item with yogurt, and it inserts it right there, breaking the link here. So that's what the insert command does. Okay, if you want to insert something at the end of the list, then you could simply say, in this case, grocery list dot insert. And how do you think you would insert at the end of the list? How do I make something point to the end of the list? I want to insert something right there. Pardon?
The sentinel node?
The sentinel node. And how do I get to the sentinel node?
Pushback.
Okay, I could use pushback, but I want to use the insert command. You're right. Pushback would work, and that's what you should use, but I'm just doing a little test to see if you know how you would implement pushback. So how can I get the sentinel node at the end? Dot end. So if I said grocery list dot end, say Brad, that would insert at the end of the list, because this would return a pointer here, and therefore it would insert Brad where I'm highlighting in black. Does that make sense? Okay, now the gentleman, what's your name? Alex was right. If you're going to insert at the end of the list, just use pushback. But this helps you kind of understand what's going on with the list. Okay? And Dr. Planck does the same thing. He actually says, instead of using push front, I could insert items at the beginning of the list by getting my iterator to point to begin, which would point to the first element of the list, and then now S will be inserted before the first item in the list. Now, clearly, it's more informative to use push front, but he's just showing again how you could insert by instead using lines.begin. Okay? So questions about insert? Yes.
So it automatically changes the pointers for you?
Yes, it automatically changes the pointers for you. And actually, there is a return value as well, although I believe the return value will be to the inserted node. So I believe that you can say something like foo, if foo was declared as a and foo would now point to would be an iterator that points to the inserted node. Okay, so sometimes you want that. So sometimes you don't care, in which case you ignore it. Okay, other questions? Okay, so it's also convenient to be able to delete from the middle of a list. Okay, so my example is, oh, sorry, question. Yeah.
If in the last example, after you inserted it, if you didn't break, and you, like, and the for loop continued, would the iterator point to the item you just inserted before?
No, good question. So the question was, if I did not put the break in there, basically you're saying, what does lit point to once the insert returns? And lit's not changed. It should point to the same item it pointed to before. So if you wanted a pointer to it, that's what I was saying. You'd actually have to declare another one and assign to it. And now foo would point to the inserted item. So if I didn't have the break there, one of two things could happen. A, there is no second milk in the list, in which case eventually I'll reach the end of the list, and you'll notice that in that case, so if I don't have the break statement here, okay, what will happen is I'll eventually get to the end of the list and I'll come out. And now what I did at the end here was that if the target item was not in the list, I add it to the end of the list. So if I kept going, my code would have a logic error because I would add yogurt twice, once before milk and then again at the end of the list, which isn't what I want.
Yeah, I was just wondering.
Okay, so, and by the way, I have no trouble. A lot of you will do things like you'll just say success. You'll create a Boolean variable and say success equals true. I'm fine with that. Okay, but it is a good idea to stop iterating at this point. So you then say lit not equal to and not success, because it is not a good idea to keep iterating once you've found where you want to do the insertion. That's just inefficient. One of the things we're trying to teach you in this course is to write efficient code. And continuing to do a search after you found the insertion spot isn't efficient. So you should try to get out of that loop, either using a break statement or using a Boolean flag, one or the other. Okay. Other questions? Okay. So moving on, as I said, being able to delete items from the middle of a list is good. So I am actually going to sort in an inefficient way by always deleting the smallest item from the list. So if I always delete the smallest item from the list and print it out, hopefully you'll agree that I will print the items in sorted order. Yes? So I first delete 1 from the list and print it out. Then I'll be left with the list 8, 2, and 10. Then I'll delete the smallest item. So I print out 1. Now I delete the smallest item, which is 2, and print it out, leaving me with the list 8 and 10. Now I delete 8 and print it out. And finally, I delete 10. So if I always delete the smallest item from the list, I should end up printing the list out in sorted order. Okay, so here's my procedure. The idea is at each step, I first try to find the minimum item. So again, I am destroying my list, which may or may not be a good idea. If I don't want to destroy my list, this would be actually a situation where I should not pass it by reference, because then it would create a copy of the list, and I could destroy the list without any adverse consequences for the calling function. So this actually could be one of those rare situations where I would not want to pass the list by reference because I would want a copy that I could destroy. But in any event, I'm assuming it's okay to do that, destroy or delete the smallest item. So here what I'm doing is I'm actually calling a function called findMin, and sort is going to call findMin. So I'm not showing you everything. I'm just showing you the important part of sort, which is calling findMin to return the smallest item in the list and delete it. So I declare or initialize my min iterator so it points to the first item in the list. Then I iterate through the list, and each time I check to see whether the item that I'm currently looking at, whether that's less than my previous minimum. If the item I'm looking at is a new minimum, then I set min equal to my current item. So when I get done with this loop, I hope you agree that min points to the smallest item in the list. Does that make sense? Okay, so now I save my return value by dereferencing min. Then I erase min from the list. So the erase method deletes an item. So erase deletes the indicated node from the list. So whatever the minimum item is, it deletes it, and then I return the value that I saved. Now, does anyone know why I needed to have this statement right here where I saved the value? Why can't I just not have this statement and just say return star min? But star min does return an integer, because that star min in this case, just a second, see right here, I was assigning to an int. So star min does return an int. Okay, but how would that, okay, save memory, so yes, I wouldn't, it's true, I would not need to allocate 4 bytes for return value, but actually there's another reason. Min no longer exists, I deleted it. Okay, if I don't have, what I'm saying is, if I don't have this statement, okay, so what I'm saying is, suppose I don't have this statement. I say boxes.size erase, and then I try to say return star min. That doesn't work so well because I just deleted min. There's no guarantee that min points to the minimum item anymore. So in order to get around that embarrassing little or inconvenient fact, I had to first save what min pointed to, then delete min, and finally return it. Okay, so questions about that? Is that, we all good with that? Okay, so you've actually seen now basically the 2 basic operations, or 3 basic operations we do on list. Insert, find, which we have to write ourselves, and delete, which is the erase method. Okay, So, the next point in the lecture is that, guess what? You can insert into vectors too, but you should not, because it is horribly inefficient to insert into vectors unless you're doing it at the end. It's very efficient to insert into the end of a vector using pushback, but it's very inefficient to insert anywhere else into a vector. So here, we've done the same code as before for reading lines from a file, except now we're using a vector. You can see we're using a vector, and here we have a iterator to the vector, and you can see that he's inserting his lines at the beginning of the invector. Okay, and it works fine, but it would run very slowly. Okay, and the reason it runs very slowly is that it has to move every item in the vector one element to the right. So if my vector looked like this, 1, 2, 3, and I wanted to insert 0 at the beginning, what I need to do is first resize the vector so that it has 4 elements. Then I have to iterate through the vector, starting with the last element, which is 3, and move everything 1 element to the right, which is what this loop does. And finally, at the end, I have a hole where I could insert 0. Okay, well, this requires n moves because I have to move every element in the vector. So if I have an input with 10,000 lines, it means that roughly speaking, each time I have to move, well, the first time I'll have to move 1 line, the second time 2 lines, the third time 3 lines, the fourth time I'll have to move 4 lines. If you remember from your class, that's n times n plus 1 divided by 2. So I'd end up with 10,000 times 10,001 over 2, or 5,000 times 10,001, which is a whole lot of data moves. Very inefficient. Okay, with insert, it takes 1 operation. I just insert at the front. So with a list, I would make a total over 10,000 lines. So with a list, it would take 10,000 moves or operations for all 10,000 lines, but for a vector, it's 5,000 times 10,001, or it's 5,000 times slower. Okay, and it gets worse the bigger the number of lines is. So Dr. Planck, to make his point, ran both programs. So he timed them, and he first timed them with his lists, and then he timed them with his vectors. Okay? And with the, excuse me, whoever is talking, could you please nod? It's actually slightly bothering me. So, or whisper. So, the list, you can see the total time is 0.01 second on 10,000 lines, but for the vector, it's 45 times slower, 0.45 seconds. For the 40,000 line file, it's 3/100ths of a second for the 40,000 line file versus 7 seconds for the vector, which is 210 times slower. So it's much slower using the vector than it is using the list. And he's using this thing. You'll often hear people refer to dev null. Okay, dev null /dev refers to a device, and null, so normally you're writing to a printer or a file. Those are all in the dev directory. But null says to take whatever the output is and just throw it in the bit bucket. We don't care. So dev null is a way of just throwing away the output. It doesn't go to the screen. It's not written to a file. It's just thrown out. So this is his way of discarding the output and just looking at how fast his programs run. And you can see a vector is horrible. So bottom line, you don't insert into the beginning of vectors. Okay, but sometimes we really do want to insert into the front of a list. It happens a lot. One of the common reasons we want to insert into the front of a list is we have a queue, okay, which is like a line. So at the grocery store, you're in a line, okay? If you think of a line, okay, people, my figures are horrible. I would have flunked art. So let's just say Brad's in line, Smiley's in line. So where do we, and now Nancy comes. Where should we normally put Nancy if this is a grocery line? Where do people enter a line? At the back. So Nancy goes at the back. But when we provide service, where do we remove people from? The front. So we're going to remove, the next person removed is Brad. Same thing with your print jobs. When you print to a printer, it puts your print jobs into a print queue. Okay? The jobs are added to the end of the print queue, and they're removed from the front of the print queue. So it's a common operation in computer science to want to have a queue where we add to the back and remove from the front. Okay? Well, we already know that it's inefficient to do that with a vector. It's actually efficient to do it with a list, but it turns out that there's something clever we can do with vectors, because if vectors take up less space than lists, so if possible, we would like to be able to have our cake and eat it too, which is be able to remove items from the back, add items to the back, remove them from the front, and still use a vector. And we can have our cake and eat it too if that is the set of operations we want to perform by using a DQ. So a DQ is a doubly ended queue, or a double-ended queue, and it efficiently supports insertion and deletion at either the back or front of the queue. So efficient operations are add, remove at the back, and add, remove at the front. Okay, whereas a vector is only efficient at the back, but a doubly ended queue is efficient at both the back and the front of the queue. Okay? And what it's doing is, most of the time, not always, but most of the time, it's doing something clever with a vector, which is, let's say we had a vector that looked like this. It had the items 1, 2, 3, 4, 5. And we remove item 1 from the vector. That, in effect, creates a hole right here when we remove 1. And now, let's say we remove 2. Okay? Well, let's say now we want to insert 6. What we could do is insert 6 right there. So what we do is we keep one pointer to the front and one to the back. And when we need to insert at the front, if we ever need to insert, if we need to insert at the front, so 6 actually wouldn't go there in that case. Whoops. Insert at the front, we just insert right there. Now it gets obviously a little tricky after we've inserted 7, what we do with 8. So I'm not going to worry about it. It's more advanced than we need for this class. But the point is, doubly ended queues are able to do some cute tricks in order to do inserts and deletes. Okay? And you may learn more about how to do that in 302 or a later course. We won't worry about it here. Just know that it's doing some clever things. Okay? But the bottom line is it's efficient to insert into either the front or back of a doubly ended queue. In fact, it's more efficient than using a list. So efficient operations are, and these operations are more efficient than the corresponding operations on a list, on a linked list. Well, I'll just say on a list. Okay, because they're operating on a vector rather than on a linked list. With a linked list, you always have to follow a pointer to the next object, and that's slower than simply incrementing an integer index. It just turns out that's the way it is. So if your operations are reserved for adding or removing at the back or front of the queue, like a printer queue, then you should use a double-ended queue. And in fact, he does some more programs using double-ended queues, where in this case he's also doing a push front, so he's reversing the list again using push front, and it works just fine. In fact, when he runs it on his different things, it's very efficient. So input 2.text, see how big input 2.text is. 10,000 lines. And you can see it runs on 10,000 lines in 0.01 second and in 40,000 lines in 0.03 seconds. And that was the same as it was for a list. In fact, we just don't have enough. 300ths of a second is so fast, it's still not big enough to distinguish between the list and the doubly ended queue. Okay, so his next example is doing the tail program where he's printing the last n lines in a file. In this case, he's printing the last 10 lines in a file. Okay, so first he's using a list to do it. So what he's doing is he's using getLine to get a line. He's pushing the string onto the end of the list. And if his list now exceeds 10 items, he erases the item at the beginning of the list. So he doesn't want his list to ever get bigger than 10 items because he's only printing 10 items. So his list never gets to be bigger than 10 items, and at the end, he prints it out. Okay, so he's adding to the end of the list, erasing from the front of the list. Okay, and he does this for all three programs or data structures, for a list, for a DQ, and for a vector. And you can see here that he is using input, let's see, he's using, I'd have to look. He's running this program, so I think he's running it on some very big list of items. And you can see with a list, it's 0.42 seconds. A doubly ended queue is just a little bit faster, and the vector is the slowest. Okay, now the vector isn't horribly slow here because we only have to move 10 items. But if the tail was bigger, like 100 items, the vector would slow the program down considerably. Okay, I'm not going to do it in class because I want to move on to the diamond hunt example, but the point is, if you need to remove from the front and add to the back, you can see here that a DQ was about 10% faster than a list in this case, and the vector was about 20% slower. Okay, so questions about any of that? Okay, so we'll end with one final example, which is he loves top coder, so here's diamond hunt. So we're hunting for diamonds in a string that has less than and greater than signs. So every time the less than and the greater than sign forms a diamond, we count it as a diamond. So you can see here that there's two clear diamonds. There's one, and here's a second one. But the problem is more complicated than that. You'll notice that it said there's 3 diamonds in here. And the reason there's 3 diamonds is each time we find a diamond, we delete it from the string. So once we find this diamond right here, we delete it, and now our string is the string that picks up here. So we have less than, greater than, greater than, greater than, less than. Okay, so that's our new string, and you can see here's a diamond, so we delete it. When we delete it, we end up with a new string that looks like that. Do you see a diamond in there? Yes. So we can create additional diamonds by deleting pre-existing diamonds from our string. That's how we can actually end up with 9 diamonds in that particular string, because each time we delete a diamond, we introduce a new diamond. Yes?
So does it only register a diamond if it's less than followed
Immediately by a greater than, yes. It only is a diamond if it's a less than immediately followed by a greater than.
Wouldn't it work the same way if it like saw a less than and then read to the next
Greater than?
And then remove those?
So yes, so if you had, no, so because if you see a less than,
Then you move on to the
next greater than, maybe. That's a
Then it would
good
take that, remove
point.
those, and read the next.
Greater than? It might work.
Because if you read the first one like that, it would still give you 3 diamonds. But I didn't know if like that's.
It might. That's not the way we're going to tackle it, but it might work.
But if there's no diamonds,
But then the pardon?
if there's no diamonds in between those two, they never get deleted, so that'll never make a diamond.
It is true, but that's why I'd have to think about it. I still think it actually works, but I'm not positive. The problem is, if you did it your way and you find this one, I guess you could remove this one and this one
Yeah,
then.
that's what I was thinking.
Okay. So that's not a strategy. I think your strategy works, to be honest, but we'd have to program it up and make sure. So that's not the strategy we're going to do. Strategy we're going to do is assume that they have to be right next to each other. Okay. So there's two ways to do it, the easy and inefficient way or the harder but more efficient way. So the beautiful thing in computer science is when the most efficient answer is also the simplest, but unfortunately that doesn't come up a lot. Oftentimes the simplest answer happens to be more inefficient. So the obvious way to do this is to simply search for a string that looks like this. And if we find such a string, we add 1 to our number of diamonds, and then we delete that substring from the string. So that's what he's doing. He's calling his string mine because of a diamond mine, right? So we're mining for diamonds. So he's saying while true, and he tries to find a diamond. Okay, if he doesn't, so if there is no diamond, you get the constant string : NPOS return. What does NPOS stand for? No position. So there is, if it's not there, you get the return value string : N position. So eventually that will happen. You will, just like a mine eventually plays out, eventually our string, no matter how rich it is, will play out. Eventually, even if it's a really rich string, it would become empty. So at that point, we simply return with the number of diamonds we found. However, if we found it, it will not be equal to string n position, so we increment the number of diamonds by 1. And then we remove that diamond from the string by finding the part of the string that precedes the diamond and concatenating it with the portion of the string after the diamond. Okay, so for example, if our string was greater than, less than, less than, greater than, less than, I would be, this is 0, 1, 2, 3, 4, so I will be equal to 2. So we first, substring will be 0, 2, which says starting at 0, return 2 characters, so that will return these 2 characters. And then concatenate it with the string that starts at I plus 2. So I is 2, adding 2, we start there and concatenate it with whatever is left. And you can see we managed to omit the diamond that we found. So that's the first program. It works, but it's inefficient. Okay? Now, you don't have to take my word for it. You have to get used to analyzing these programs and figuring out how long it takes them. So in the worst case, where do we find the diamond? At the very end of the string. So if there's n characters in the string, in the worst case, we're going to have to look at n of them before we find it. Okay? So if the worst case, it turns out, is going to be the one that looks like this. Okay, in that case, we'll always find it in the middle of the string. And then we'll delete it, and we'll have to put together this string. So every time we're concatenating together, and not only does it take us maybe n characters to find it, but then we have to concatenate together n minus 2 characters. So the find may look at up to n characters, and the concatenate may have to look at n minus 2 characters. Okay? So if there's nd is the number of diamonds, we may look at up to n plus n minus 2 characters. That's pretty inefficient. Okay? If ND is on the order of n, which it is for this string, if there's 8 characters in this, if there's n characters in this particular string, how many diamonds are in that string? Pardon? Half. N divided by 2 diamonds are in that string. So ND could be of the order of n divided by 2. So if we substitute n divided by 2 in there, that's equal to n squared over 2 plus n squared over 2 minus n, which is roughly equal to n squared minus n. Pretty inefficient. Do you see how, though, I analyze that? That's the important thing. The find, if I look at the end of the string, is going to take n characters. If I remove 2 characters from the string, that means I concatenate together 2 strings that in total are equal to n minus 2 characters. Hence, the find is n, and the concatenate is n minus 2. That's not very efficient. A more efficient strategy, okay, he actually times it. And he's doing it with strings that look like this. So the first time he does it with a string of length 10, and it's very fast. Even with a string of length 1,000, it's only 1/100th of a second. But when he jumps up to 100,000, which is a factor of 10 increase, he goes from 0.01 to 0.79, which is a jump of a factor of 10 almost. And when he goes from 10,000 to 100,000, he goes from 0.79 seconds to a minute 19 seconds. That's horrible. From 1 second to a minute 19 seconds, that's a degradation of over 120 times. So this thing is getting pretty bad for very rich strings. So we're going to try a second approach. And here's what he's going to do with the second approach. He is going to try to find a diamond. Okay? So if he finds a diamond, which he's done here, he's going to, first of all, he's going to dump the string into a list. Kind of like with gold, right? We filter the gold. We dump the gold, the dirt, into a shaker, and we shake it out, and what's left is gold. So here he's dumping all the characters of the string into a list, and then he's going to go through the list looking for a diamond. And when he finds a diamond, he's going to delete it from the list. So when he finds the diamond, he is going to delete it from the list, which is what he did here. So you can see that going from here to here, he's deleted it. So now his new diamond, he's formed a new diamond, which is right there. Okay, so now he's going to delete that new diamond. So you can see he's deleted this one and this one down here. So now he's at this point in the list. And when he gets over to here, he finds that diamond. And he deletes it. And now you can see all that's left is that, and it doesn't match anything, so he's done. So that's his plan. So what he's going to do, going back to the top, he's going to keep pointers, one for left and one for right. So left is going to be a pointer to a less than symbol, and right is going to be a pointer to a greater than symbol. So if he finds that he has a left that is pointing to a less than and a right that's pointing to a greater than, he's going to delete those two characters. And after deleting, you can see he's going to have to reset his left to point to the character that was before the deleted element. So here, left was here and right was here. Once he deletes these two, he needs to move left back so it points to the item before the deleted diamond. Right? Does that make sense? Okay. The only other thing he has to worry about is if the diamond occurs at the beginning. If the diamond is here at the beginning of the list and he deletes it, if he made it point to the previous item in the list, what would it left point to? The sentinel node, and that's no good. So if the diamond is at the beginning of the list, he actually has to make left point to the first item to the right of the deleted diamond. So if he's at the beginning of the list, he must move left to point to the first item to the right of the diamond. If he's anywhere else in the list, then he moves the left so it points to the previous item in the list. So here's his code. Okay, so left he sets to the first item in the list. And he's going to keep going until he reaches the end of his list. Okay, so if left is equal to a right diamond, that's no good. Left has to point to a less than, so he simply increments the left iterator until he's basically iterating left until it points to a less than. Then when left points to a left, then he sets right to be equal to left. So he's got, if this is his list, he first made left point here. Actually, make this a greater than. Left first pointed there, then he moved it to point to there. Left now points to here. So now he makes right point to left with this statement right here. And now he increments right to point to the next one. So if he's got a diamond, right will now print to a greater than sign. So he says, first of all, he has to check to make sure he hasn't stepped past the end of the list. If he's past the end of the list, we're done, right? So if left was right here, then right would point to the sentinel node. So his first check is to make sure that he's not at the end of the list. Okay, so he's not. He's actually right here right now. This is where he is. So his next check is to see if right is not the termination of a diamond. So if right is another left arrow, it's no good, and he increments left. But if right is equal to a greater than, he increments the number of diamonds. Okay, the first thing he does is reposition left. So this repositions left. So if left is at the beginning of the list, he says new left, he moves it to the right of the current diamond. These two statements do that. If it's anywhere else in the list, so if beginning of the list begin of list move left to the right of the diamond, otherwise move left to the left of the diamond. And he still needs to do something with left, which is why he has this temporary variable new left. Because he still needs to delete the characters that left and right point to. So he still needs left to point to the less than character, which is why he has a temporary variable called new left to point to the new left. Then he erases left and right and makes left point to new left. So questions about that? Okay, so next time we will move on and start considering sets and maps, which are yet two more data structures that allow us to efficiently organize data. So we'll take that up on Thursday.